Well, good afternoon, everybody, and welcome to NASA's Johnson Space Center. We're here to talk about the status of Space Shuttle Discovery and the STS-133 mission. Joining us today is Bill Gerstenmaier. He is the Associate Administrator for Space Operations based out of NASA headquarters. Also joining us is John Shannon. He is the Space Shuttle Program Manager. We'll hear from both gentlemen, and then we'll take questions from JSC, KSC, and then out on the phone bridge. So with that, I'll turn it over to Bill.
All right. Thanks, Kyle. First of all, I'd like to say, John and the whole shuttle team have just done a fantastic job of working through this problem. They're methodically looking at all the data and the analysis. They've laid out a really excellent plan to get through this problem and understand what's going on. It's an extremely well-ordered plan with the high priority items first, and it looks really good. The teams at KSC have done a great job. They've completed the repairs on the tank and completed the x-rays that will provide critical data to the analysis teams and to John's folks that are looking at all this stuff. We would have liked to have found a most probable cause by now, and things would be a lot more straightforward. This is turning out to be a little more complicated from an analysis standpoint, and it doesn't lend itself to a very easy answer. But again, I think the teams are working through this methodically. They're not going to rush to any kind of conclusions or any decisions that are not right until they've really got those supported by good data and analysis. So they're continuing to do that, and we'll see how things come in the next several days. We thought we'd like to talk to you today just a little bit to give you a status of where we are. We haven't talked to you in general for a while. We're not going to be able to answer all your questions because obviously the teams are still looking at data. We can kind of tell you where we are, what's going on, what's happening. John will give you a lot more details. We'll be careful not to speculate because especially at this time in an anomaly resolution activity, things change pretty quickly. The right analysis comes in, the right data comes in, and then we're off on a slightly different path. So we'll be careful not to speculate too much about where we're going and where things are heading. And again, we're going to do like we do with all these problems. We'll let the data drive where we're heading. We won't pick a particular launch opportunity. We'll be aware of where the launches are, but we'll let the data, the analysis, and the work in front of us kind of drive where we go. So with that, I'll turn it over to John, and he'll give you some more details. John?
Okay, thanks, Bill. Yeah, like Bill just said, we got out of our last big engineering meeting with participation from Johnson Space Center, Marshall Space Flight Center, Kennedy, our independent engineering and safety groups to talk about this external stringer crack. And I haven't really talked to you since we first had this on November 5th on our first tanking opportunity for STS-133. So let me just kind of orient you as to what we're talking about. Of course, I have the shuttle stack here, and at the top of the external tank, you have the liquid oxygen tank, and you have the liquid hydrogen tank that's down here, and the structural member between the two is called the inner tank, and we're talking about an inner tank stringer crack. And the way this inner tank is built up is there are 8 rounded panels that when they're all assembled together, they make the circle that will sit on top of the hydrogen tank and connect it to the oxygen tank. And the 8 panels that make this up, 2 of them, one on each side of the solid rocket boosters, are called thrust panels, and they're made out of 2-inch thick milled aluminum. And they're supported to a beam that goes between the solid rocket boosters, and they carry most of the load when the solid rocket boosters lift off. And it's transmitted to those thrust panels and throughout the stack. The other 6 panels, there's 3 on each side, 1, 2, 3, and then on the back the same 1, 2, 3, are made of a thin aluminum sheet, and that sheet is stiffened by these stringers. And the stringers are U-shaped pieces of an aluminum lithium material. They're 21 feet long, and each of these panels, each of these 6 panels has 18 stringers, about 21 feet long, that run down the length of the panel to give it stiffness, much like a corrugated tin roof material or the wavy piece of cardboard inside a cardboard sheet stiffens it up. That's the design. And what happened is these stringers are attached to a ring at the top and a ring at the bottom that is supporting the tank, the liquid oxygen tank up here and the hydrogen tank down here. And what happened on November 5th is when we started filling the liquid oxygen tank with the minus 300 degree F liquid oxygen, the ring that the stringers are attached to shrinks radially about 1/2 inch. And I'm not going to point this anymore, so you can. I promise not to do that anymore. So when that whole ring shrinks, you get a bending at the top of those stringers, and the stringers are fastened by rivets in the middle and then these special fasteners up at the top. And as that ring shrinks, the top of the stringer bends, and the design is such that it just bends in, and it doesn't really take much load other than that. What happened on the first time we loaded the tank is when that first bending moment started on the stringer, a crack appeared along one of the feet of the stringer, and the stringer basically cracked on the other side in an overload condition and popped out about 1/2 inch, which would mean the stringer was straight while the rest of the tank bent in due to that cold shrinkage. Now, when it popped out, it broke the foam, and we saw a U-shaped crack on top of that stringer area, which would have been a violation of our launch commit criteria. And when we dissected that foam out, we saw the cracks in the stringer. We went to either side of it, found smaller cracks in the stringer to the left of it, and then we went out further until we found good stringers, and the investigation started. And as we started looking at it, we have had history on these stringers during assembly occasionally of getting cracks in them that are caused, we believe, by the assembly process. If you look at the design, and we've reviewed over the last week and a half very closely the design of these stringers, how they're assembled, how they're attached, the loads they would take in the initial cryo loading, and also during launch, they have plenty of design margin. So a properly assembled stringer in the expected flight environment will not crack. And when we started looking at the data, these stringers, which we changed the material on about 43 tanks ago, we changed the material from aluminum to an aluminum lithium, which is a more brittle material. So that's over those 43 tanks, that's about 5,000 stringers that we have assembled. And out of those 5,000 during assembly, we've had 31 cracks. And we started reviewing those today at the engineering review. And it can be due to things like the fastener misalignment or damage, getting hit by something during the assembly process, mishandling. But all of them have been known assembly issues that we've had that have caused those cracks. It's not a design issue, and that's something that we have re-verified over the last week. Again, if a stringer is properly assembled, it will carry that load and not have a problem. So the question was, we had this crack that appeared on the launch pad. It was the first time that it happened. Did we have, the two questions are, did we have an escape in our inspection methods that allowed a flaw to get into the assembly of the inner tank that was exposed when we did our cryo loading and loaded up that piece? Or the other question was, did you have some kind of an assembly misalignment that could add additional stress to that piece, that when you added the stress of cryo loading, it would overload that piece and you get this crack? Now the hope last week, and why we were kind of sequentially slipping launch dates, was that we would show that there was a flaw in this material, that you could go find some material defect that got through our process, that was a very unexpected event. And we also hoped that the initial cryo loading stress on that part would be the maximum stress that part saw during the entire flight phase. The loading was going to be more than the ascent itself. And as we're going through the investigation, it's neither one of those points is as clear as we need it to be to commit to go fly. To keep our options in front of us, we repaired the two cracked stringers with the certified process that we would use if we found those cracks at Michoud assembly facility where we put the inner tank together. And we used our certified process to refoam the area. So basically, if these cracks would have happened at Michoud, we would have fixed them exactly like we fixed them on the pad, and we would be in a position to go launch. But we have an unknown here is how did something get through our process and get to the launch pad to allow a crack? And then do you have a susceptibility to have another one of those kind of conditions? We looked a lot at the loading from the cryo shock that you get and that initial bending and whether that would envelope. Right now, it's not clear that it envelopes our flight environment. It looks like it does for some part of the stringer, but during the launch phase, you move that stress to another part of the stringer, and cryo loading does not appear to screen that other area. So if you had a flaw there, potentially you could induce a crack in that area. So that wasn't as clear-cut as we wanted it to be. We used fractography to look very closely at the stringer to see if there was some existing flaw or some pre-existing crack, and that was inconclusive. We could not find anything in there that said, yes, clearly this is where it started, and it propagated out of there. So we're back to looking at, is this something that could have been hidden from the guys that were looking at it, like an assembly stress that was loaded into the bending stress at cryo load. So where are we? It's a complex problem. If you think about it, you're putting it through a very difficult environment where you have thermal stresses, you have bending stresses, you have tension and compression when you're lifting off. And the team has done a great job so far of modeling all that and helping us understand where our vulnerabilities are in that stringer design. We have worked really hard, and I think the main focus for the program right now is to understand the exposure. We have to show a few things. One is, can you assemble a part and not induce a crack that would be seen by our examination methods, but it would be enough of a stress that when you cryo-loaded, you could induce a crack. Now, after we got this condition, we used an X-ray machine up on the launch pad, and we were able to look at every single stringer on the orbiter side to look for additional cracks, and we didn't see any. We've gone through all that data, and it looks really good. So what you would have to have is either an assembly error or a part error that didn't get through your inspection process, or that got through your inspection process without being identified, would not have cracked during cryo loading, but could potentially crack under the stress of a launch. And then you have to talk about your exposure. If that happened, could it crack the foam? And then if that could happen, could that foam be dislodged and hit the vehicle, which is what our main concern is. You also have to do a fail-safe analysis to say, all right, if I structurally lost one of these stringers due to a latent failure, could I induce a crack on another one and lose that one? And could that propagate down? And how many stringers, could I lose and still not have a structural problem? That work is still going on. So, the team is looking at fault tree analysis to make sure that we look at everything from assembly and production, from when the part is initially made to how it gets to the assembly area, to how it's treated at assembly, how it's fastened onto the panels, how it's transported, how it's primed, how it's foamed, how it's integrated into the tank, how it gets to Kennedy Space Center. Every single piece of that inner tank's life is in the fault tree for how you could potentially induce some damage. We're doing a lot of data mining on previous cracks to understand what assembly methods led to those cracks and if they were potentially, if they could potentially have caused this crack. We're looking at a lot of testing with stringer material and inner tank material to try to induce flaws or induce stresses in it, and then put it into a stress environment and see if it can crack as well. We're doing a imagery review. Our flight history on this part of the tank, where up at the LOX flange, is extremely good. We have not lost foam from that area that we know of. We're going back to make sure that we look at all of our imagery to see if we've ever had cracks up there that we could not explain. The initial pass to that was that we have not, but we're going to look at it again. So that's the case. We're kind of pulling all together, all this data. You know, do you have some kind of an assembly error or a flaw that could propagate into a crack? At what point could it propagate into a crack? What would be the impacts of that? Can you screen it with cryoloading and this X-ray? You know, and then if you didn't catch it through all that, you know, could you end up losing some foam over the top of that area and damaging the vehicle? So we went through all of that analysis today, and we're not quite there. I handed out a lot of homework assignments to the team to go collect data, and we really need to understand our risk. While we had cracks that occurred at the assembly plant and were repaired effectively, we don't, you know, this is the first time it happened at the launch pad, so we have some kind of a process escape that allowed this to get to the launch pad in the first place. So we need to understand our risk. What is the risk that something else could have gotten through our process and gotten out to the launch pad? And there's a lot of things on the table. We potentially could instrument the vehicle and do another tanking test so that we would understand the stresses in that area even better and could further improve our models to know what is our exposure to risk. Do we really understand what kind of a screen you get through just the cryoloading technique? We may end up deciding that we need to get some X-rays of the backside of the tank. That's not available to us on the launch pad. So if we had to do that, we would roll the vehicle back to the VAB and put the platforms around it and get that data, if that's data that we thought would help us in determining if this problem is okay. So we're going to develop the stress models and do all our testing and look at all of our assembly methods and pull together that whole story to understand what is our risk exposure here. And if we can't get enough data to show that our risk exposure is acceptable, then we're going to have to look at other options. And those might be that you go in and you have to modify some of the tops of the stringers, or you have to do some further X-ray methodology, or you have to run some kind of additional tests. So it's really clear to me that the team has identified all the different areas that we need to work through, either through analysis or test, to identify what our risk exposure is, and what the final results of all that analysis and test will be, I don't know yet. And what we told the agency leadership is clearly we're not ready for the December 3rd through 7th window that's coming up. Over this next week, we'll be a lot further down the road in each of those pieces that I identified. We're going to leave the option open for the next launch window, which starts December 17th. But a lot of data has to come together for us to support that. The team, I don't think the team is worried about any specific launch date at all right now. They're just worried about getting the proper data so that we can determine what our risk exposure is to this problem. And once we determine that and determine what the appropriate path forward is, then we'll go off and pick the right launch date. And that's it.
Okay, great. Well, let's see. We've got a limited amount of time for Q&A, so if you guys would ask your best question, we'll try to get through everybody. I've got a number of people out on the phone bridge as well and down in KSC, but we'll start with Mark and then take Eric.
Sure. Mark Carell for Aviation Week. Could you bound the end of the December 17th launch period and maybe bound the next one as best you know it?
Yeah, the window mark is December 17th through the 20th, and all 4 of those days are okay. If we go past the 20th, we would be flying for our nominal mission over the year-end rollover. Basically, you go from day 365 to day 1. And we have procedures to be able to configure the on-orbit computers appropriately so they can talk to the ground computers. But we would want to do those procedures during a quiet period while we're docked to station. So after the 20th, we'll have to look at the on-orbit timeline and pick out which days we could launch so that when we went over the year-end rollover, it would be a quiet time on orbit and we could do our computer reconfiguration that was required. So there's some days between the 20th and December 31st that we could pick up launch dates, but we haven't sat down with the operations team to define those yet.
And we really haven't focused very much really on the launch stuff. We'll do that later once we get a better handle on where the problem's going and where the work is going. And there's some options we could do even in the beginning. If it helps us some ways, we could even potentially launch before the Soyuz docks if that provides some assistance to us, and then hold off. So I wouldn't get hung up on those specific dates. We'll spend a little bit of time working those at the right time later once we get a better understanding of where the data analysis is going and where the work is going, and then we'll talk more about launch dates. But that's the general period that John described.
Eric?
Just so I understand the primary concern, is it that you would get a crack after the sort of post-tanking inspection of the tank that would be invisible, and that crack would sort of manifest itself in the foam during the launch process and break off a piece of foam? I mean, is that the primary thing you're worried about?
In general terms, yes. Remember, we have tanked this vehicle, so we put a pretty good stress on those stringers, and we've x-rayed them all to make sure they don't have cracks, and none of them have cracks on the orbiter side. So what we're worried about is a flaw or assembly issue that did not crack during the cryo loading, but could potentially crack during some higher stresses in the flight environment, and then that could propagate into the stringer coming off of the skin panel, pushing out the foam, and then the foam coming off and hitting the vehicle. So that's what we're trying to screen for.
Okay, let's go down to the Kennedy Space Center in Florida for some questions there.
Marcia Dunn, Associated Press. I'm wondering what happens after December 31st. Could you take a shot at January? And given, Christmas, New Year's holidays, and all the overtime that might entail, why not just put it off now until January or February, whenever that next window might be?
Yeah, we've kind of looked at all those options, and there's nothing there that's, again, driving us. We're not constrained from a financial standpoint. We're fine from a budget standpoint. We'll do what's right to make sure we're ready and safe to go fly. Our primary purpose is we've got cargo that needs to get to space station. It's critical for space station operations, and we'll figure out the time the shuttle is ready to go, and we've got the right mix of cargo to go fly, and we'll pick the right dates. So we're kind of looking at this December window first, see how that fits. And then beyond that, we've got some opportunities in January, some in February. Another consideration for us is the shuttle performance. Ascent performance generally gets worse as you head towards February. So we have to be careful from a shuttle lift standpoint. We may need to make some cargo changes on the shuttle depending on when we launch. So we'll work that with the station program. We'll work that with the loads people, and we'll make sure we balance all those things to find the right opportunity to launch consistent with having good rationale and good data to go fly.
Quick follow-up. What's the critical cargo that's driving all this?
There's all the spares that are on the shuttle. There's some in the mid-deck. The permanent MPLM is there with a lot of items on the inside. Some of the ones that come to mind are we have the distiller assembly, which is the piece of the urine processor that helps make urine into potable water. That's an important piece to go up. There's a catalytic bed that purifies the water on board space station. That's also another consideration. But there's lots of others. So, these flights are really packed with all the critical spares for station, a whole variety of them, and we just need to make sure that these flights get there with those critical items.
Kevin Oliver with WFTV in Orlando. Just curious, with the previous cracks that you've noticed at Michoud, were any of them cracks on stringers that were both next to each other, like on this case?
We're still mining the data. My understanding is no. The cracks we've seen at the assembly plant were assembly related when they were putting them together, or handling related. You bang it against something and you get a gouge or a mark. That's another piece of the analysis that's ongoing is the initial crack related to the crack in the stringer next to it, and the initial structural models indicate that it is. But there's going to be continuing work on that to make sure that that's really true. And the working theory is that when you remember, these stringers are attached to this big thick flange at the bottom of the tank, and when the one stringer released its energy, that it put enough of a pulse into that flange to crack the stringer next to it. This aluminum lithium material is a very strong, very lightweight material, but it is not ductile at all. It's like 3% ductility, so it's a very brittle material, and it is not tolerant to impacts or a lot of loading beyond the design of it. So it's not a real forgiving material, and when you're assembling it, if you make a mistake, you end up having to replace pretty much the whole stringer. So.
Okay, well, let's take the calls that are out on the phone bridge, and I'll call on you in order that you called into the newsroom. Start with Bill Harwood.
Yeah, hey guys, it's Bill Harwood at the Kennedy Space Center. For John Shannon, just to be clear, at this point then, you don't think this is a generic issue with the aluminum lithium tanks. You think it's an assembly issue of some sort, and you're trying to bound that. Have I interpreted that correctly?
That's heading into speculation. That's our working theory right now. If you look at the design of the stringers, they have very good design features and acceptable capability to handle the normal load that you would expect from cryo loading and ascent. And the only cracks that we have found at Michoud are related to assembly or mishandling. So I think that's where the X-ray of all of the stringers after we cryo loaded it is critical. If we would have found other cracks or other problems, then we would think that yes, we were right on the edge of our design margin, and we had cracks all along. There is nothing to indicate that. We looked with that X-ray at all of those stringers that had gone through the same bending moment, and we have sufficient capability through that X-ray to determine if there are any cracks, and there are none. So, absent the fact that we don't have any other cracks in there, it makes you think it's a localized phenomenon. Now, for me to sit here and say that we had a flawed part or we had an assembly issue is, that is cutting out probably 80% of the fault tree that we're going to methodically work through. We want to make sure there is nothing specific about this tank, nothing specific about this inner tank, nothing specific about the way we processed it, to make sure that there's nothing special that we did in that area that could have caused this. But what is fair to say is that even after cryo loading, we've looked with the X-ray, we don't have any other cracks. The cracks that we have seen during assembly were all due to assembly or mishandling. So that's the data that we have right now, but we need to really, really rigorously go through our fault tree.
And just one more quick one. Can you wait? It's kind of a follow-up to an earlier question from the Houston Chronicle. In terms of the risk of foam separation and then structural failure, I mean, is structural failure really an issue here? I mean, I thought that was a pretty beefy structure, and even if I realize you don't have the answers to this yet. I'm just trying to understand if those are equally weighted in your mind or if the real threat primarily is the foam debris. Thanks.
Right now, we're doing our homework, Bill, but what it looks like is that the highest stress area of the stringers in cryo loading or in flight is the top 9 inches. And we believe that we could lose multiple stringers capability and not have a structural issue. We have to do that work to understand it. because you don't know what your exposure to some assembly process or materials process or a flaw is. We'll do that work and understand that. I believe that it's going to show that we have quite a lot of capability in that inner tank area, and it's going to be a discussion on having an escape that allows a flaw in there that only surfaces during flight, not during cryo load, and that movement of that stringer due to the cracking causes foam to be exposed, which could be lost and hit the vehicle. And I think that's where our risk posture is going to be the highest, and we have a lot of work to make sure that that's really true, and then B, to really understand what that risk exposure is.
Okay, let's see. Robert Perlman.
Hi. Given the uncertainty of a launch date right now, can you talk a little bit about how crew training and crew preparation, based on changes to the mission and the flight plan, is proceeding? I mean, when we were launching during this current window, you were going to only have 3 people on the station, so there would need to be changes to meet that. Now, if you launch on December 17th, you'll have 3 new crew members on board who may not have trained to support this mission. How are you managing crew training? Thanks.
And what the teams have done is they're pretty remarkable. When we didn't do the first launch, and we knew we were going to potentially launch to a period when there was only 3 crew on orbit, they went ahead and took some of the tasks that were going to be done during the dock time frame. For example, the carbon dioxide removal assembly. You saw last week, or this week, I guess, or last week, they actually took that apart and removed the beds out of that device. That was going to be done during the docked mission. So they offloaded work that was going to occur during the docked time frame and moved it up into the time frame when the shuttle wasn't launching. So they've really optimized, and they've taken many tasks like that and they moved them forward in the timeline, and they got them completed ahead of the time. So when the shuttle actually comes up and docks, will be in a much better configuration to support the transfer activities, support the critical activities that have to occur while the shuttle is there. So the teams have done a remarkable job of kind of balancing, looking ahead, planning ahead, and actually scheduling work earlier to get it done when they had the time to go do it. So I think they've done a very good job of balancing it, and we provided multiple options to make sure we've got the right crews trained, the right folks ready to go do the activities during the mission. They also looked at things timing-wise that, there's a HTV, a Japanese transfer vehicle coming up. There's an express or exposed logistics carrier that sits in the cargo bay that was going to hold some of the items from the HTV. They've worked out a plan that if that's not there, they can still offload the HTV and work things out. So again, the teams have done a remarkable job of planning ahead, looking ahead, optimizing to make sure they're ahead of things. So just as the teams on the ground are doing all this data analysis, getting us ready to go fly, the ISS team has been off balancing all these things to make sure we're still in a good posture to go do the work that has to be done when we actually get there with the shuttle.
Okay, let's see. Denise Chow, space.com, are you on?
Hi, yeah, Denise Chow, space.com. If the data comes back such that a mid-December launch is possible, would the 11-day mission and all its objectives stay intact, or would something need to be altered? And also, someone mentioned that there may need to be cargo changes, and I was just wondering if you can maybe state what those might be and what potential impacts it might have to the space station.
For the December flight, there'd be no cargo changes, and the mission duration would be just the same as we've been discussing before.
And if it was in February?
If it goes to February and we would have to offload some items from the mid-deck, or we could potentially make some other cargo changes.
Okay, let's see. John Bracken, are you on the line? Okay, let's see. Ken Kramer, are you on the line with us?
Yes. Hello. Hi, Ken Kramer for Spaceflight Magazine. Thank you. Just have a question to clarify. You have checked the entire stringer on the orbiter side from top to bottom, yes? And I'd like to know how certain you are that these techniques would actually detect a crack, because the way I understand it, these cracks were detected visually.
Okay, Ken, what we have done with the X-ray is we've looked at the top area along the liquid oxygen tank where the problem was. We've gone all the way around the orbiter side of the tank. We don't have access on the launch pad to the back side. So we've looked at the liquid oxygen side, probably the top 2.5 feet of it. We have started looking at the liquid hydrogen side just to make sure that there's no issues down there. That work is ongoing. We haven't looked at the stringers, the riveted areas of the stringers in here, but they're very low stress areas of the inner tank. And what was your second question?
How certain are you that these scanning techniques would actually detect a crack?
Can you see it?
The way I understand it is they were found visually.
Right. There are features in the X-rays that are very small that give them a lot of confidence that if you have an open crack, that you would easily be able to see that in the X-ray. You're right. The initial cracks were found visually because we didn't have the X-ray system out there yet, and we knew we were going to remove the foam and take a look at it. So we just got on with that. And I will tell you, the X-rays are pretty amazing. There was a discussion of whether there was a feature in one of the stringers that we looked at, and it was actually a primer paint streak that you could see in the X-ray. So the fidelity of it, or the ability to see very small features, is very good with these X-rays.
Thank you.
Okay, let's see. Eugenie Reich, are you on? Nature Magazine? How about James Dean, Florida Today?
Yes, thanks, Kyle. John, how fortunate do you feel that foam did crack as it did on the 5th during tanking, even though that was secondary to the reason for the scrub? Obviously, I guess without that happening, you might not have found the issue at all before another launch attempt.
Yeah, I don't, fortunate or unfortunate, I wouldn't characterize. It's just, if something gets through our process, if we have a process escape, you always want to find that before you lift off. And this, once we finally determine what the root cause of this was, and we go make sure that we don't have any other exposure to it, that there's no other process escape that could manifest itself in the same way, then we'll be a safer program. So it's good that we saw this. Our pre-launch scans would have definitely picked it up, even if we had not had the hydrogen gaseous umbilical carrier plate leak. And we would not have launched because the foam crack was in clear violation of our launch commit criteria. And like any violation, we go and assess it and make sure that even though that problem may be fixed, like we think this particular stringer is fixed, you make sure generically you're not exposed to that same risk anywhere else, and that's the process we're going through right now. So it was good that we found it on the pad. I think even though our process did not catch this in the assembly, if that's what it was, certainly the launch commit process would have caught the foam crack.
Anything else, James?
Of the tanking test, and it sounded like you mentioned that entirely in the context of stringer modeling rather than the GUP repair. And so I was wondering if you could just talk about the reasons why you would do a test and just kind of what would be the general time frame and pros and cons.
Well, we need to nail down our risk exposure to this, and is there something out there that can get through our process that can cause this condition? And in the interest of, we need to determine a lot of different data through test and analysis. I put on the table that if a tanking test will help you, then let's certainly give consideration to doing that and being able to fill in some of the unknowns. And one of the ones I was thinking about was that it's very hard to model the stress and the loads and the stress on that particular part due to thermal deformation, due to compression from the tank filling up with liquid oxygen. it's a pretty complex model, and they've done a nice job on the finite elements model. But if we don't understand it well enough, well, let's go instrument it. Let's go inside the tank and put strain gauges in. Or we talked about, hey, we could remove some foam and go put instrumentation on those stringers, and you do a tanking test, and then you've anchored your model in really good, accurate data, and then you understand what the stresses are on that piece. So I did not, I was encouraging the team that let's make sure that we understand what data we need to understand our risk exposure. And if we need to do something like doing a tanking test, then we're going to go do that. If we need to do something like rolling the vehicle back and taking a look at the backside of the tank with the X-rays or anything else, I'm trying to leave the options very wide open to the team to go identify what data they need, and then we'll identify the best way to go get that data, and then we'll understand what our exposure is to this problem.
Is there time for a quick follow-up, Kyle?
Sure.
I guess I wanted to clarify do you feel what is your confidence that the GUP issue is completely resolved? Because obviously that was what initially caused the scrub, and if that happens again, then even in this next window, then it looks like you're off till February. And then finally, what are you doing with your other two tanks to assess the issue? Whether the stringer issue could be a factor for them as well.
Yeah, I'm going to answer all the questions. As far as the GUP issue, we learned a lot because we went slow and carefully thought through the disassembly and took a lot of measurements and tested and found out that we had a requirements problem. When we set up the alignment between the quick disconnect for the GUP and putting it through the plate, we had a misalignment requirement, but we did not require where in a 360-degree circle that misalignment could be. And it turned out that it was in the worst place it could have been, so that the gravity loading of the vent arm exacerbated that misalignment and made it even worse. So we had a requirement for how far off you could be, but we didn't say where on the 360 degrees that misalignment could be. Even though we did all that work after STS-119 and after STS-127, we did not clue into that. And I think that was the root of our problem on 133. And the team has come back. They're very aware of that now. They've done all the work required, and I'm very confident that the GUP is fixed, and I would not require a tanking test before committing to a launch attempt just for the GUP. If we do a tanking test to gather data on the stringer performance, then we'll get the GUP for free, which is always nice. I would draw a parallel. If you remember, when we initially had the problem, it was on Friday for the GUP problem, November 5th, I think it was. We still had a launch opportunity we could do on that next Monday. And the team came in and said, wow, it's a big leak. It's probably something obvious. We can run out there. We can just go swap out some stuff, and man, we can be ready to go and make a launch attempt on Monday. And we sat back and thought, no, we have a process. We're going to go through this very methodically. We're going to make sure we learn as much as we can about it, because we have a couple more flights that we would like to fly. And let's learn as much as we can and not be exposed to this in the future. And there was nothing that was significantly wrong with the GUP. It was a stack up of tolerance issues that caused the leak. And by going very slowly and thinking about it and being very methodical and giving up on a launch opportunity, we were able to solve that problem. This problem is exactly the same. You could say, hey, we're just going to go do the repair that we always do. We're going to refoam it. We're going to go launch, and we're going to be in good shape. We have to understand what our exposure is to that problem recurring somewhere else on this tank. So we're very carefully, very methodically going through it, and we're passing up some launch opportunities to do that. But that is appropriate, because we want to make sure that we fully understand the problem before we commit to go fly. And that's just the way this team has been working, is that they do the work that is required. Bill doesn't give me any, and Mike Suffredini doesn't give me any kind of pressure at all that, hey, we need to launch because station needs, X, Y, or Z component. They always tell me, hey, just get it right. When we launch, and the station will be happy to see you when you show up. So the team has been very methodical. is working through this very carefully. They understand completely what I expect of them, and that is to make sure that we do the absolute best risk assessment that we possibly can, and we'll make the decision after that really good risk assessment is done whether we can fly with the design we have right now or if we need to go make some modification to it. And if we do, we do, and we'll go execute that, and we'll fly Discovery when we're fully confident in the ability of the tank to support the mission.
Okay, we're back here we have time for maybe one or two more. Mark?
Thank you, Mark Carreau, for Aviation Week. As best you can you sort of sketch out at least your sort of management level milestones for following the process?
Sure. Well, I'll just tell you what's the next week, because I don't know past this next week, right? I told everybody to take tomorrow off, and a good part of the team is going to take Friday off as well. Most of this team has been working since the initial problem on November 5th, so that's like 4 straight weeks, weekends included, just killing themselves trying to understand this. Told them take tomorrow off, take Friday off if you can. We'll start on Saturday. We're going to work through all of the homework I gave them on the data mining of the cracks, the loads and stress analysis, the debris potentials, make sure that they do the fail-safe analysis, work through the fault tree. All of that work that I outlined will start on Saturday. We'll do a checkpoint with the team next Thursday at another PRCB, Program Requirements Control Board. And what I think we'll probably do is end up giving Bill a heads up on Friday as to where we think we are in the investigation. So it's, I think we've done a really good job of outlining exactly what work is required. Now it's just turning the crank and making sure that all of that work is done. We do all of our peer reviews on it. We do our independent checks on it, and then make sure it's quality data, and then we'll be able to make some good decisions.
And Eric, we'll let you wrap it up.
Eric Berger with the Houston Chronicle. I guess finally, is there any scenario under which you might find that the existing tank has to be changed out? I mean, I know you don't have any, or it would be difficult to replace it, but is that a possibility, or is that something you don't foresee happening?
I don't know right now. We have to understand our risk exposure with the current assembly process and design that we have. All 3 tanks were built the same way, so there's no real difference between the 3 tanks. The only way I can envision that we would swap tanks is if we did all of this homework and we decided, you know what, we don't have enough information to say that we don't have an exposure to the same thing happening. You can't screen it well enough, you can't show through NDE well enough, so you have to go in and do some kind of a modification on that flange to beef it up somehow. And I've got a team going off and thinking about that. Well, it may be that doing one of the other 2 tanks that are at Kennedy Space Center would be quicker. So we would go and modify a tank, and then we would fly Discovery first on that tank that's modified. That's a long way down the road. If we can't get comfortable with our risk exposure, potentially we'll start talking about that. But that's the only way really I can see that we would swap tanks. There's no real difference between the tanks.
No, and I think the good thing is John and the team, they've laid out a very methodical process of which way to go. And then there's some things they pointed out today that look like they're pushing us in one direction or another, but then John asked the team, this is really critical analysis. Let's go back and make sure we really understand those pieces. So when they do some double checks and triple checks, I think out of there somewhere more than likely will come the answer. It's just going to take a little bit of time and patience for us to get through it. They've been very methodical. They went back and x-rayed all the tanks in the VAB. So we did the same thing in the VAB. We looked at the oxygen intertank region and the hydrogen intertank region to see if there were anything we saw in those tanks, and we didn't see anything there. So again, I think the teams have a very methodical process. We'll kind of let the data drive us, as John said. If there's some advantage potentially from a schedule standpoint of swapping orders or things, we'll see that. But I think the thing right now is to just kind of let the teams run. They've got some good work in front of them. Let's take our time, make sure we really got it right. We know what the critical analysis is. We know where the critical tests are. Can we add some more tests to give us more confidence? And then I think it'll become pretty obvious which way we need to go.
Okay, that's all the time we have for this briefing, but shortly, if you'll stay with us on NASA TV, we're going to head over to Mission Control up to the International Space Station and climb aboard with the Expedition 25 crew. Commander Doug Wheelock of Expedition 25 is just about to hand command over officially to his colleague Scott Kelly, who will be the commander of Expedition 26. Doug Wheelock, Fyodor Yurchikhin, and Shannon Walker will be heading home tomorrow, but they'll conduct that change of command ceremony here at the top of the hour, so stay tuned for that. And then tomorrow, of course, Thanksgiving Day, those 3 crew members that I mentioned are going to be heading home in their Soyuz spacecraft. The coverage is staged in various points throughout the day, beginning at 3:30 Eastern Central Time, 4:30 Eastern, with the farewell and hatch closure, and that'll be followed by the undocking, and then late at night the deorbit burn and landing. The deorbit burn scheduled for 9:54 p.m. with landing at 10:46 p.m. Those are Central Time, so stay tuned to NASA TV tomorrow while you enjoy visits with your family and friends. And for all of us here at NASA, happy Thanksgiving tomorrow. Thank you, guys.